Okay, let's do the moment of inertia of a uniform rod. So let's put that integral to work and actually figure out, take an object that's solid. Let's actually decide where we're rotating around, calculate the moment of inertia. And there's a general strategy that you'll always use when you do this. So let's take a rod here, simple rod, and let's assume it has length L and mass M. The first thing I can do with that, if you think back to when we were doing, and I think this is a really important step when you're doing this, if you have something that's uniform, or even if it's not uniform, you want to think about like writing the density of the object in some way. And so when you're dealing with a rod, you would be talking about the linear density, right? That's like how much mass per unit length it has. That's going to be really important. If we were dealing with a 2D object, we'd be talking about the mass per area, and a 3D object would be what we think of as regular density, which was mass per volume. And I think it's always just a good first step. You're going to need it down the line. Write an expression. Lambda, the linear density of the object, is just m over L. Now, I'll show you another way to think about that in case you don't like that, but that's a good way just to think about how to start. So I have this, it has mass m, length L, and I'm going to rotate it around its center, which also happens to be its center of mass. And so if you think about it, then this point all the way down here is negative L over 2 relative to that origin, and this point over here is L over 2, and I'm setting my origin at the center. First thing I want to do is write my expression that I'm going to use. So the moment of inertia I is equal to the integral of r squared dm. But now we have to put down like a coordinate axis and get this all visualized. So since we're in one dimension, I don't really need r. I can use x, right, as my axis. And I can think about a little piece of mass dm right over there. That's at a distance x from my rotation axis. And it doesn't matter whether it's on the right or the left. The beauty of this squared is that it's going to all work itself out. The negatives will go away. It'll all come out in the integral. So now setting the limits of integration, I'm going to do once I represent dm in terms of x, because then I could think about meaningful limits of integration. Right now it's just sort of generally across all of the mass, but you really want to turn that into something you can work with. So r is going to become x squared. That's an easy thing to see because that's my distance from the rotation axis. But my problem here is I need to represent dm in terms of something that is in terms of x so that I can do this integral. And so if I come up here and I look, I say, well, I know my linear density, mass per length, is sort of telling me the kilograms for every meter. And I could think about this little dm as having a tiny width dx, right? That's how wide it is. Then dm should be equal to lambda times dx, right? The linear density, how many kilograms per meter, times how many meters, which is that tiny little bit of space that this has. If you don't like this, or if you find this a little confusing, sometimes what people do is they just do a little ratio, which I'll do up here as an aside. They'll say dm is to dx, since it's a uniform rod, as m is to L, and then you just multiply up and you get dm equals m over L dx. So you could do it that way too. So either way will work. You get the same thing. So now I come back to my integral, and I'm just going to do it. I is equal to the integral of x squared, because that's my distance, times dm, which is m over L. That's a constant. I'm going to be able to pull that out, times dx. And so that equals m over L times the integral of x squared dx. And now I have to set my limits of integration, and my x is going to go from negative L over 2 to positive L over 2. Now I remember my integrals that x squared dx is x cubed over 3. So this becomes m over 3L x cubed evaluated from negative L over 2 to L over 2. And now I just have to plug in my L over 2. So my moment of inertia is m over 3L times L over 2 cubed minus negative L over 2 cubed, which is equal to 2L cubed over 8, if you do that algebra out, times this, which was m over 3L. So this was what was in the parentheses there. Now I get my moment of inertia, and I just do it out a little bit more and do some cancellation, and I get that this equals ml squared over 12. And that's the accepted moment of inertia for a rod about the center of mass. Okay, next thing.